Good. You can hear me well, right? Or is it
I can hear you.
okay? Then I can start. Yes. I will talk about the parallel and multi-threaded functions, and today for Julia. So I will be grateful if you could, in the survey, tell me something about this session. What can I improve? And if you think that this is too easy, too difficult, or one needs more material, so let me know because it is very useful for me just to know. So we will learn what is pair programming, why do we need it, and when can we use that, and follow some tools that we have at the centers just to monitor the usage of resources. So I included this session of parallel programming because, as you noticed in the previous lecture, I was talking about serial codes and parallel codes with Julia, how to run that in batch mode, and to make it a more or clearer. Yes, I included this session of parallel programming. So in parallel programming, one executes a different task on different computing units that are called also cores, and we do it simultaneously. Yeah. So previously, in the 70s, 60s, even 80s, huh? So the CPUs contain only a single core, right? And the tasks were executed therefore serially, so one after the other, right? That's why in the earlier machines, if one started different programs, one could see some delays in the applications. But now, for instance, in the machine that I am using currently, so one can see that one has several cores, right? So in principle, on this laptop that I have, I can already run some jobs in parallel mode that are split into different cores, in this case 8, yeah? And so that the task is distributed, yeah? Uh, across these different cores. But if you want to go beyond this number of cores, or maybe your application is heavy, right? And you don't want to slow down your older programs like the browser or ThinLink or anything else, then it's a good idea to go to an HPC center like a HPC2N or UPPMAX or NSC and so on. Yeah. So here I depicted two of the most frequent programming models. And the first one is called the shared memory. And here the main feature is that the different cores, yes, share some local memory, which has a high bandwidth, so it doesn't cost that much to transfer the data back and forth. Yes, and therefore one can achieve a fast uh, code with this programming model. However, this is limited to the architecture. And for instance, on Kebnekaise, we have some nodes that have up to 128 cores, and they share some memory. But if you want to go beyond 128 cores, then you need a different programming model than shared memory. So if you want to scale your code beyond that. And one way to do that is by using distributed computing. And here, instead of sharing the memory, one transfer the data through some uh, internet connection, yes, which is fast enough, and one can transfer the data so that the course can be updated with new data. Yeah. So currently the machines are more complex than pure share or pure distributed memory, because as you can see here, already some cores can share some local memory, which is fast enough, but also one can transfer messages through some protocol. And in the last lecture, I mentioned NPI, and one can use also other approaches like the distributed package in Julia. This is a node, how it looks in Kebnekaise for a node with 28 cores. And these cores share some memory, as I mentioned. So if you want to go beyond this type of nodes with 28 cores, then a distributed programming model is needed. So why do we need, or why do we need a programming model? So as you have noticed in the previous lectures, so we have a cluster where there are several computing nodes, right? And each node contains many cores. And I mentioned previously that on Kebnekaise there are nodes that contain up to 128 cores that share some memory. And in order to benefit from all this computational power, you need to make your Julia code aware for all this hardware, right? According to some protocol. So, but once you start using the HPC clusters, uh, one can incur in some difficulties or in some situations like underusing or overusing the cluster. And this is something similar that happens with the laundry machines, right? So in the laundry rooms, in some places, right? When one reserves the laundry machines, and one can reserve many of them, but at the end of the day, one uses only a single one. Yeah? Or in the other way around, imagine that one requests only one machine, but one fills the machine with many things, and that is overusing the resources, right? So we need to get to have some manner to monitor the resources, and this is especially critical for parallel computing, because here you can easily over exceed or under use the cluster. So in our clusters, we have some tools to monitor the usage of resources. And previously, I mentioned how to use the job usage command on HPC2N terminal. Yeah. So this can help you to see the CPU and GPU utilization and also the memory utilization for the requested nodes. Yes. And on other centers, they have a different feature. And here, one can connect directly to the computing nodes. This is not possible on Kebnekaise. And here one can do an SSH directly to the node. And there one can use the top command or htop to see if the resources are being used properly, right? So maybe, for instance, you requested 20 cores, but your simulation is using only one, yes? So it means that in your project, you are wasting some computing hours. Yeah? That's not critical because you are not paying in terms of money, right? But anyway, you are losing some priority because once you consume your core hours, the priority of your job will be reduced. So I mentioned previously in the previous lecture, yes, the thread program supported
Your
and
sound is breaking up for me.
well supported for Julia. Can you hear me?
No, I can.
Yeah, you can hear me. Okay, so and then these two these programming models are supported in Julia, yeah, and in particular in Julia there are some packages that contain external libraries or can contain external libraries, right? And they have already some implicit parallelization layer that can be activated with some external variable. And for instance, here I mentioned the OMP threads that create some threads, right, for the libraries, in particular for this LAPAC Blast. And that's why I included, yes, the picture of underusing or overusing your code, your allocation. Because here easily, for instance, if you parallelize your code with Julia, but at the same time, each worker in Julia uses an external library that contains also some threads, yes, activated by some variable, for instance, this one, then you can over exceed the resources because this number of threads in Julia and the threads in the external library are multiplied. Yes. That's why I consider this is a warning, and then you can monitor the usage of resources with this command or even top or htop. This is a realistic situation. So imagine that you have some linear algebra operations and the variable for the threads in the external library is set to some number, but then you use a Julia that is parallelized by Julia threads, and then the number is multiplied, the number of threads from Julia and the number of threads from the external library. So this is also interesting in the case of Julia that here you can have the so-called Julia threads, yes, that are native to Julia, but there are also some threads for the external libraries. So you shouldn't confuse the threads from the libraries to the threads from Julia. Yes. So in the case of threading programming, one common problem is the data racing, because as I mentioned previously, in thread programming, the threads share some common memory, and that's why they can at some point create some conflicts with the data because maybe some threads want to write at the same time on the same memory address, and then the results will be uh, unuseful, even though the simulation runs faster, right? So how to set the number of Julia threads? Notice here the Julia threads, different from the library threads. So we start Julia on the command line with the dash dash threads options, and this X is the number of threads. In the threads package that I mentioned in the previous lecture can be used to parallelize your code by using threads from Julia. In the case of distributed programming, we saw before that here the processes don't share the memory, but instead they can send and receive messages. And there are some packages in Julia that support this programming model. One of them is the distributed package that I mentioned in the previous lecture, and I provided you with an example. And also, one has the message passing interface MPI that also supports the distributed computing. But here, one thing is that you need to know MPI beforehand, right? And this is not something straightforward, right? So if you are starting with the parallelization, I would recommend the distributed package that is native for Julia, or the threaded package that is also native to Julia, and you don't even need to install any additional package like MPI. But in the previous lecture, I show you how to install the MPI package in Julia. So if you choose the distributed package, then you can start Julia with some number of processes, and you can do this on the terminal by using the dash P, and the X here refers to the number of processes. So notice the difference in the nomenclature. Here for distributed programming, I use Julia processes, and in the threaded programming model, one uses the threads, Julia threads. In the case of big data, there are several tools that you can use for Julia. One of them is Dagger, and this tool is inspired on the Python tool called Dask that supports distributed arrays and can be used for very large arrays, right? And there is also a possibility of parallelizing the computations by including some Julia threads or Julia processes. Okay, so I will spend some time on this demo, right? And here I show you the simple for loop, which is language agnostic. And this is a common situation that we can have in research, right? Where one has one big for loop, or maybe one has many for loops, yes, as is it shown here. And the wait function, notice here, it's a agnostic, language agnostic. It only simulates some task, yeah. So to avoid any further code, right? So I just put wait here to simulate a task that takes 1 second. But you can put something more complicated here if you want. So then if I execute this for loop as it is here, so then I will observe this situation. The first task will take 1 second, the next task 1 second, and so on. In total, it takes 4 seconds. But because there is no data dependencies in this for loop, just notice here that I just need to wait 1 second, and the one iteration doesn't depend on the other. Yeah, and in this case, I can split this loop by using 4 workers or 4 threads, or in the nomenclature of the hardware, I can split that in 4 cores, as it is here, and then each core or CPU execute one single iteration, and therefore the overall time can be divided by 4. Yeah, as you can see here, instead of 4 seconds, it takes about 1 second. This is the parallel version. And here I give you an example in Julia. Yeah. So I am using the threads package that I mentioned previously. We don't need to install it because it is part of the base installation in Julia. So, but if we want to monitor the timings of the functions, I recommend this package, which is called benchmark tools. And this one you will need to install because it is not part of the base library. So then I define the number of iterations with this 4 in this case, but you can change that. So then I create a function in Julia that is called sleep serial, and it takes just the number of iterations. And here I write the for loop, and the waiting function in Julia is called the sleep in this case and this function will sleep for 1 second. Yeah. So in total, this one will sleep for 4 seconds. And then I call the btime function, which is included in the benchmark tools. And this will time and benchmark the serial function. Yes, this is the number of evaluations and samples that the benchmark will do. Yeah. So this is to avoid many repetitions of the btime function or macro. Yeah, because otherwise btime will try to repeat the simulation many times. That's why it's called benchmark macro. Yeah. So here I put the parallel function with threads in Julia, and I call this function sleep thread. And notice that the only difference that I need to write in this function is this decorator, which is called add threads. And then this function will be split into the number of threads that I request. And for timing the function, I also call the macro btime with the same number of evaluations and samples. So how to run this script? So first you load the Julia module on the terminal. So we did it already. Then we need to create a script that we can call, for instance, sleep threads, and it's already there. You see that it's the same function as I have here. And we can write a batch script as I did in the previous example, right? In the previous lecture. But because this is a short job, it doesn't take longer than a few seconds. I can also run it by using the srun command directly on the terminal. So I can do this, copy, then the paste, and I need to fix the project ID. And for HPC to N is HPC to N 2025 062. I don't remember if it needs the colon, but I will leave it. And if it is giving errors, I will remove that. So notice here that for threads, I am specifying one task, which corresponds to the execution of the Julia script. And I also need to request the number of cores that I want for each Julia threads. And in this case, I will be using four threads only, or four cores. And I start Julia with this number of threads. Again, that's why I included the picture of underusing or overusing your cluster, your resources. Because here, imagine that I request four cores, right? But in Julia, I forget about this and I request 20 threads. So it means that the threads will be oversubscribing the resources that I have requested here. On the other side, imagine that I think that my program scales well, or I forget about that, and I request 40 cores, but I made a mistake or something happened, and finally I request only one thread, right? So in this case, I will be underusing the resources. So in order to make it optimal for this example, I know that I need four threads, and then each thread can be executed on a single core, and that's why I request only four cores. So then I execute this by typing enter, and notice here that this job is queued, yeah, and it is not running on the login node, and this is something that you need to do, not to run on the login node, but submit the job to the queue. So you see that the job has been allocated, yeah, and when it finishes, it will print out the times. So this was for the thread package, and you can also do that for the distributed package, and the script is here, and you can try this. Let me see what happened. Okay, you can see here that I make a mistake. I need the benchmark tools, yeah, in my Julia, but I haven't installed that, yeah, for this Julia version. So I can add it, benchmark tools. And again, notice that I use the srun command on the terminal because this was a relatively short job. Yeah. But if you need to run this, yes, and the job takes hours or even days, then you can write a batch script with one of the templates that I mentioned in my previous lecture, and then you can submit that with the sbatch command. So now this should be there, and I can submit this again. So remember that with this number, you can use the job usage command after the job starts running. and then you will see the statistics on the web browser. And notice that it takes some time, yes, and although you only need to perform this operation for a few seconds, what is taking some time is loading the packages and doing the job that Julia needs, yes, in the background. So when you run the first script, you can see that it takes 4 seconds for the serial function and 1 second for the around 1 second for the second function where I use 4 threads. So this is the basic idea, and you have something that is more complicated. You can start with this and go step by step. We also recommend to start with a serial code that is working. So don't start with a code that you don't know if it is producing a good result, right? And also when it produces some good results and you want to parallelize it, then it's recommended to have a clean version of that is documented and also that contains uh, pieces of code that are enclosed in functions like this, right? Rather than writing a for loop that contains many lines of code, right? You can split the code into features, yes, and see what of these features needs to be parallelized and can be parallelized. In this case, the situation is simple because this data or this function doesn't depend on the iterations. But imagine that you have an array where the iteration I depends on the iteration I plus 1. Then this can be more challenging and you will need to find some way to tackle that. And that is not always possible, right? But if you don't have any data dependency, then you could try these approaches. This is for the threaded package, and this is for the distributed. It's doing something similar. But in the case of the distributed package, one uses the decorator distributed. And one also need to add this sync macro here. So in the exercises, you can see how to run your code efficiently. This is an example for a 2D integration, and one is trying to parallelize this integral, the 2D integral of a sinus function. I like this one because I know that the result must be 0 or close to 0. Yeah? So the Julia code is here, and I will use the distributed package. Here you need to fix the number of workers, yeah? And the number of workers can vary according to the instructions from 1, 2, 4, and 14, and so on. And here there is a batch script, yes, where you also need to fix the number of tasks that are needed. So remember that if you request one task, then the optimal way without oversubscribing the resources should be one worker, right? And so on. In this example here is a more elaborated example, and it's more realistic. And you can deal here with a data frame. where some operation it needs to be done on the entries of the data frame, and these operations can be parallelized. Yeah, so this is something more realistic that could be used in a research workflow. But this is just the basic also. Yeah? So you can try this and let me know how this is going. Yeah. And also don't forget the evaluations. So let me know any comment about this material if you don't understand something, or if you want to see something else. I will be grateful. Thank you. So you're gonna start with the exercises until, let me see.